Well, today we have an opportunity to explore the wonderful world of robotics, and our guide is Professor Brian Scassellati. He will be showing us some of his research. Some of you have gotten to see it already, and I think you're going to really enjoy yourself. So before he comes to the podium, let's just show our appreciation for him, okay?
Well, thank you, everybody. I build robots, and I brought a couple of them with me today, and I'm going to show them to you in just a little bit. But before I do that, I want to show you a picture of one of my favorite robots. This is a robot that works around the clock doing an incredibly important job. It sorts hot dogs. And it sorts hot dogs so fast that when it's moving, all you can see is a blur. It has one little mechanical arm that goes over and uses air pressure and a pair of suction cups to pick up hot dogs as they come up this conveyor belt. And then it spins them around and puts them down in a nice, neat row so they can go through a plastic packaging machine. And that robot is faster and more accurate and works for longer amounts of time than any person on the planet could. This robot runs for about 364 days out of the year, 24 hours a day. Okay. It does what most robots do incredibly well. It's fast, it's accurate, and it's reliable. And this is what most robots in the world do. They do jobs that what we think of are as sort of the 3D kind of jobs. They're jobs that are dirty, dull, or dangerous. They do things like weld car doors on an assembly line, or go off to the surface of Mars and explore other planets. Or they crawl through sewage pipes to inspect them, things I definitely don't want to do. And they go and they dispose of bombs and check for explosives. This is what most robots and most of robotics is based around. It's based around building machines that do jobs that we as humans find dirty, dull, or dangerous. But those aren't the only robots that are out there. And in fact, these aren't the kinds of robots that I build. Okay. I build robots that are designed for a very different kind of environment. I build robots that are designed to interact with people. That is, I don't care whether they're incredibly fast, and I don't care whether they're very, very accurate. And I don't care how many hot dogs they can sort in a minute. But I do care about things like, are they safe for people to be around? Do they know that when I yell at them that they should be quiet and maybe go hide under the bed? We build machines that try to live and interact in the same worlds that we do. And that means we can't sort of put safety tape around them and protect ourselves from them just by distance. And it means they have to understand something about us. Now, we already have a lot of robots that live in our homes already. Some of you have probably seen some of these. Some of them are toys. They're things like the Furby or the Aibo. They're little robots that we use to play with. Some of them are robots that do useful tasks. They vacuum floors. They mow our lawns. But most of these robots, when it comes down to it, are kind of dumb. They don't really pay attention to what we do. And when I yell at these robots, they sit there and they do the same thing they were doing before. They don't really listen to me. They don't really pay attention to what I want. And I can't change the way that they act. They're not terribly good friends or partners or coworkers. They're more like tools. They're things that I can use for a very specific job. Now, there are a lot of companies out there that are starting to think about how to build robots that are more involved in your life. And this next picture is actually from an ad that Honda was running in the New York Times for a number of weeks. And here it shows their robot as part of the family. This is a robot called Osmo, and you're going to see a video of it in just a minute. But a lot of people are starting to think about how we can build machines that live in the same kinds of spaces that we do, that can learn from us, that can interact with us in the same way that a good human partner would. And so what I'm going to show you today is I'm going to show you some of the robots that we've been building to try to understand how to build these smart robots that could live with us and do things with us, rather than just being our tools. Now, the good thing about this is these robots work on a set of very simple principles. They work on a set of principles that are built into all of us as humans. But let me show you first what we already know how to build. So this is a robot called Osmo that was built by Honda. And it runs. And it looks kind of funny in the way that it runs, but it really does run. And this is one of the things that we're good at. We're good at building machines that do something over and over again, that do things very accurately, just like the same way that the robots that sort hot dogs or weld car doors. Yes? It does look like a guy in a suit, and it was designed to look like a guy in a suit, really. Okay. These machines are very good at doing what they're doing. This is a little video clip showing you that he's actually running. The difference between walking and running is when you run, there's a one point in time when both your feet are off the ground. If you're walking, you always have one foot, or at least one foot on the ground. And now you'll see him doing a couple of other little things. But this is the kind of engineering that we're already very good at. We're good at building mechanical devices that do specific things. Now, unfortunately, this robot doesn't know when to run, and it only runs on very flat surfaces, and only when you tell it exactly what to do. Here he is running around in a little circle. Robots like this today, they don't usually pay much attention to what's around them. They're programmed to do something very, very specific. You'll see him running once more, and then in a second you'll see him run around a set of cones. Now the thing of Osmo is, he's programmed to do exactly that. And if you do things like you move where the cones are, he's not smart enough to look out and see that that's where the cones now are and that he should change the way he's running. He just runs in exactly the same pattern over and over again. All right, so here he is running down the slalom course. Okay. What we want to build instead are machines that can actually pay attention to what's around them, that can understand something about the physical environment and the social environment that they're in. Now I'm going to stop the video in just a second before you all get mad at me. I'm going to let you know in advance. Okay. So one of the things that we rely on is the fact that people are very good at understanding the world around them. And in fact, we're so good at doing this that we can't help but do it. So when you watch this little video of shapes moving around on a screen, you see a story. I can ask you which two of these are friends, and you can answer me. And I can ask you which one was frustrated. Which one was frustrated? Yeah. Which two are friends? What were they playing? Okay. How did you get all of that from three triangles moving around on the screen? Your brain is very good at being able to pull apart all of these little bits of information and to build a story out of them. And so when you look at even very simple things like these shapes on a screen, your brain is able to build up a story about friendships and about what these triangles are thinking and what they're feeling, even when all you see are these little tiny bits of movement. So it's no surprise that we should be able to build robots that can do some of the same thing. If we really want to be able to build robots that can be in our homes and interact with us, they're going to need to do the same kinds of things that we do. And so what my research group does is we try to understand the ways in which we can build robots that are social, that could live with us. And in order to do that, we found that we have to understand a little bit more about how people are social. And so we use these robots to understand a little bit about ourselves. So today I'm going to show you 3 different examples of how we use these robots to understand a little bit about people and what we've learned from doing that. Okay, so here's the first example. Sometimes we use these robots as models. Let me tell you a story first. How many people have seen a dog chase its tail? Yeah, that's the easy question. Okay, here's the hard question. Why do puppies chase their tails? Why? For fun? How about when they bite them at the end? Are they still having fun? No. Why do they chase their tails? Why? Yeah, they see this funny little thing flashing around there. It's kind of furry and it's moving fast. And hey, that might be a squirrel. I should go catch it. And they spin around in a circle trying to catch it. And then they chomp down on it. And then they squeal and go hide under the rug. Now, the puppies do this because they don't understand that that thing that they see back there is their tail. They don't understand that that's part of themselves. If they did, they certainly wouldn't bite it. Human infants have to do the same kind of thing. They don't have tails, but they have to be able to figure out that these things in front of them, that they belong to themselves, that they have control over them. Now, I'm a computer scientist. And in computer science, the normal way we would try to explain this is to say, okay, well, what I have to do is I have to learn about what my hand looks like. And I have to remember what it looks like so that when I see it another time, that I can remember it and say, oh yeah, that's my hand. And then I'll know not to bite it. Now the problem with that, though, is that this looks like my hand, and this is also my hand, but it doesn't look the same, and so is this, and there's all sorts of other gestures you can make, and it still looks like your hand. But it doesn't look the same. It's not the kind of thing where I can test it quite that easily. So I have to have some other way of figuring it out. So you guys are going to figure it out for me right now. How do I know that this thing is my hand? And I need you to put your hand up. And how do I know that that's not my hand? It's not attached to me. That's a good start. What else? What else? Yeah, I have to learn where my hand is, and I have to build up some kind of expectation of where it is. But the easy thing is, one of them moves when I tell it to. And one of them, well, hopefully moves when I tell it to, but doesn't always. So here's how I could figure it out. I could try to move my hand. And if it moves when I tell it to move, then that's got to be part of me. So we've been trying to do this with our robots. We use a robot that's over in another building here at Yale. Its name is Nico. And it's designed to be the same size as a 1-year-old child. It's small. And Nico right now only has an upper body, doesn't have any legs, so it's kind of bolted to a table. But it's got 2 arms and a head and a torso. And one of the things that it has to be able to figure out is to figure out that those things moving around are itself. This is a problem that we call self-other discrimination. You have to be able to discriminate which things are yourself and which things are somebody else, some other. Okay. So these are 2 pictures taken from Nico's cameras. Nico has cameras in its eyes, and it looks out at the world, and it tries to move. And it looks for things that move exactly when it's telling them to move. And so when it sees things out there in the world, like it sees Kevin, one of my old students, and Kevin's moving around, but Kevin doesn't move when the robot tells him to move. But the robot can also see its hand, and that moves when he tells it to move. And the robot also right now is seeing itself in a mirror. And what do you think? Does the thing in the mirror move when you tell it to move? Yeah. So this robot, when it sees itself in a mirror, says, hey, that's me. And when we talk about this to our friends in psychology, they get very upset. They say, no. That can't be right. You've got this simple little machine. And all it does is it looks for these sort of matches in time. That can't be right. Because we use this test to see whether or not animals are self-aware. We test them by seeing whether or not they respond to a mirror, whether or not they know that that's themselves in a mirror. And there are very few species that actually do that. And when we come along and we say, wait a minute, we've got a robot and it does that too. And it does it if you put it in front of a carnival mirror that's all distorted, and it does it even if you try to fool it, you can't. And so sometimes when we build these robots, one of the things we learn is that we can have a very simple way of doing something that changes the way we have to think about what it means to be social or what it means to be intelligent. And so maybe these tests that we're using aren't quite as good. All right, let me give you a second example. We do a lot of work with the Yale New Haven Hospital and a group called the Child Study Center, because we've used these robots for a number of years to help kids who have social deficits. These are kids with autism. How many of you have heard about autism before? Yeah, virtually everybody. Okay. Kids and adults with autism have certain communicative and social deficits. They don't know some of the same rules that you and I all know. They don't know that it's not okay to go up and talk to somebody when your nose is this far away from them. If I sit here and I stare at the clock and I stare at the clock and I stare at the clock, eventually you guys are all going to look up at the clock, because you know that I'm thinking about that and it might be important. Individuals with autism don't do that. They don't recognize that your tone of voice has meaning, that if I sound angry, that I am angry. And so we use robots as a way of helping them and a way of trying to teach social skills to them. Yes?
I have autism.
You do? Excellent. I'd love to talk to you. We use a robot called Pleo. And I'm going to show you one of these guys now. This is a little dinosaur robot that we use, and we reprogram him to do things that actually help us out. So Pleo is a little dinosaur. And when we use him in the clinic, I use a remote control to tell him what to do. And so I'm going to tell him right now, see, we'll put him up there so you guys can see him. I can tell him that he should be a little sad. And I'm going to give him my microphone for a second. And he doesn't sound terribly happy. And I can also tell him that he should be happy. You ready for this one? And I can program him to do anything that I'd like, and I can control him just with a simple remote control, just like you control your television. Okay. When we bring Pleo into the clinic, we use him to train certain abilities. Like we tell everyone that Pleo's afraid of water. And we put him down on a mat where he has to cross over some rivers. And every time he gets up to a river, he goes and he looks very, very sad. You gonna be sad for me? There we go. And when he does look sad, we ask people to encourage him, to say something that sounds encouraging to get him to cross the river. And not only to say the right words, but to say it in an encouraging tone of voice. So I couldn't say, "You can do it, Pleo." That wouldn't quite work. But if I went ahead and said, "You can do it, Pleo, come on," then he'd cross the river, And then eventually, after he'd succeeded, he could go ahead and do his happy dance again. This is one of my favorite crowd control techniques. I can just do this over and over again, and you guys will just keep laughing. Okay. After we're done here, we've got a bunch of Pleos here, and you guys can come down and have a look at them and hold one of them and take a look. But for now, I'm going to put him away so I can talk about some more robots, okay? Okay, so one of the things we find when we use him in the clinic is that we find a lot of kids are very receptive to talking to the robot. They're very excited to interact with the robot. And we often see kids displaying novel social behavior with the robot that we don't see them using when they interact with adults. Okay. Let me get to my last example here. Sometimes it's just interesting to put robots out there and to see how people respond to them. And this is especially true with really little kids. Because robots, like the ones we build, like Pleo, they're sort of at the boundary. They're not really alive, but they are active and engaging. They're not really intelligent, but they are interactive. And so we use these to sort of challenge people to see exactly what their definitions are and what kinds of social behavior they generate. Okay, so let me show you first. One of the robots that we use is this little yellow snowman called Keepon. And I'm going to have you guys take a little survey test with me right now. Okay? I'm going to show you 3 copies of Keepon dancing. And what I want you to do is I want you to figure out which one is the best dancer. Okay? So we'll do a couple of these, but whoa, that's not good. Not too loud. There we go. So let's go ahead and we'll see which one is the best dancer. You ready? Okay. Okay, so how many votes are there for A? Oh, nobody. How many for B? How many for C? Very nice. All right, we're going to do 2 more, and then I'll tell you about the results here. All right, so you ready for the second one? All right, here we go. Okay, how many voted for A? And how many voted for B? Oh, an even split. Excellent. All right. All right, you ready for the third one? All right, here you go. Here's our third and last one. So you got 3 choices this time. All right, let's see. Last vote. You ready? How many voted for A? How many voted for B? And how many voted for C? Oh, good even distribution. All right, I like that. Okay, so in the first video that you saw, the difference between the robots was in terms of their timing. Some of them were on the beat, and some of them were off the beat. And one of them was on beat about half the time and off beat about half the time. And the overwhelming sort of choice there was for the one that danced on the beat. If I'd have asked you instead, which one is the most human-like dance? I asked you to pick the best dancer, and you all picked the one that was on the beat. When I ask everybody, who's the most human-like or most realistic dancer, usually people pick the one that's only right half the time. In the second and the third one, or in the second one of the robots danced with basically an individual joint movement and then another individual joint movement. And one of them danced sort of doing all of it together. And people are pretty evenly split on that because they're all still kind of cute. And in the last video, you saw 3 different ones, and they had a different number of dance moves for each robot. One of them had 5, one of them had 7, and one of them had 9. And you guys all liked the one that was about 7. The one in the middle. And that's not because you couldn't tell the difference, or at least not from what our experiments say. It's because we like the ones that sort of do some of the same thing over again. We like to see that repetition, but we also like to see variety. And you sort of stuck yourself somewhere in the middle. So let me break now, and I actually brought Keep On here today, but it's going to take me a second to wake him up. And then I'm going to do another experiment with you. So don't get settled in too much. We're going to need you to sort of help me with this one. So Keep On is a little guy. And I'm going to switch over now, and I'm going to wake him up. And when he wakes up, he has to stretch a little bit. Okay? And so I'm going to go ahead and wake him up. And let's turn him on. Oh. Here we go. So he's going to move around and stretch a little bit. And then I'm going to ask you to help me out with an experiment that we've been doing. We've been trying to teach Keep On how to dance and how to do a better job dancing. And to do this, we've been trying to use some of the same strategies that video games use. So we built up a little representation, and I'll show you that over here, that looks like Dance Dance Revolution. That is, you're going to see little Keep On figures slide across the screen from the right to the left, and when they get to the box, you need to do one of the things that Keep On can do. That is, to lean to the left, or lean to the right, or to bounce up and down. Okay? So, like I said, I need your help with this. So, if we have the dancers here, could you guys stand up? We'll try this out. Everybody stand up.
Hey, good to see you guys.
Okay, so what you're going to see is the same interface that we use with our subjects when they come into our lab. And we're going to ask you to do the same things that they have to do. So I'm going to start the song, and then as the things slide across, you're going to have to lean to the left, lean to the right, and bounce up and down, and we'll teach Keep On collectively how to dance. You ready? All right, here we go. Ready? Here comes the bounce. Bounce, bounce, and lean. Bounce. Can I shut off the other mics?
It's this one.
Keep-On did pretty well on that time. And so when we bring subjects in, we have them dance with the robot, and the robot then gets a score based on how well they've done. And we ask them then if they want to teach the robot again or if they want to try another song. Let's try one more song. Okay? One that I think the adults will remember. Oh, we're going to do this one more time. Hold on here. We'll give you one more shot with this now that you can hear the music.
Oh, wait.
1, 2, 3, 4. And lean. All right, quick switch. 1, 2. All right. Oh, it can't get better on that one. So when we bring people in to do this in our lab, we give them a number of different songs that they have to try. And if you want to try some of the others with us later, come on down and we'll have some more keep-on training sessions. But what we're doing when we're looking at this is we're actually not really too concerned about how well the robot learns to dance. What we're actually interested in is how we can make people be willing to teach these robots. And I just got all of you to stand up and teach a little yellow snowman how to dance. And that's actually going to be something that's very important because when you bring a robot into your home, you're going to need to teach it which dishes it's allowed to touch and which ones it shouldn't. And you might have to teach it that stepping on the cat's tail is a bad thing. Okay? And so we're going to need robots that can learn very effectively from people. And we're going to have to build them in a way that people don't mind teaching the robot. Okay. I'm going to show you one last example, and then we'll let you actually come around and see the robots. And this is a story about one of the most successful robotics projects ever. This is a robot called Minerva that was built at Carnegie Mellon. And Minerva was the solution to a problem that people in robotics had worked on for about 20 years. For about 20 years, we were worried about how to get robots to navigate from one point in a room to some other room. Because the robot had to figure out where it was, and it had to figure out how to get from point A to point B. And so a group of very smart people got together, and they put together a number of years of work into building a solution to this problem. And they got the right answer. They built something that really did work. And to demonstrate that, they built this robot Minerva, and Minerva was about this tall. And they took it to the Smithsonian, to the Museum of Natural History in Washington, D.C. And they programmed Minerva to be a tour guide. And so they told Minerva, what you should do is you should go out, get a bunch of people, and then lead them from one exhibit to another. And that'll be a great demonstration that this robot knows how to get around and doesn't get lost in this enormous museum. And so on the first day, they brought the robot into the museum, and they put it out there in the middle of the entrance, right next to the great big woolly mammoth there. And they turned it on, and like all good engineers, they then ran away and hid and watched what people did with their robot. And so when the robot started up, all of a sudden everybody came across and they looked at it and they said, oh, look at this. It's this big, interesting thing. And a group of people gathered around it. The robot turned on, woke itself up, and it said, hi, my name is Minerva. Would you like a tour? And it was programmed to sit there and wait for somebody to say yes. And as soon as it heard yes, it said, great. And it would pick out a set of destinations, and it would say, please follow me. Now, the robot was also programmed to be safe. The robot was programmed so that it wouldn't run into things. And it had a ring of sensors around it, so it could tell when it had somebody in front of it. And it was programmed so that if you walked up in front of somebody, that you should turn and move around them, and then go where you were supposed to go. And so when this group of people gathered around Minerva, Minerva woke up and said, "Hi, my name is Minerva. Would you like a tour?" And somebody said yes. And it looked and it said, "Oh, great. Please follow me. There's a person in front of me. I better turn." And it turned a little bit. And it said, "Wait, there's a person in front of me. I better turn." And it turned a little bit more. And it said, "Wait, there's a person in front of me." And after about 5 minutes of spinning in a circle, they turned Minerva off and they took it away. And they thought about this and they said, okay, well, what we've got to do is we've got to recognize when there's a group of people around us. Okay? So the second day, they brought Minerva back out, turned Minerva on, ran away and hid. And somebody came out and said, "Hi, what's this? This is an interesting robot here." And everybody crowded around. And the robot woke up and said, "Hi, my name's Minerva. Would you like a tour?" And somebody said yes. And the people gathered around. And Minerva picked out a set of destinations and said, "Okay, please follow me." And it looked and it said, "Wait, there's people all around me. I better ask them to move out of the way." And so it said very politely, it said, "Excuse me, could you please move out of my way so I can lead the tour?" And the person right in front of the robot stepped out of the way. And the person who was behind them now said, "Hey, I can get a good look at the robot," and they stepped in. And Minerva tried to turn to get out of the way and said this again and still got nowhere. And so they turned it off and they took it away. Now they were getting desperate. And so they said, all right, we've got to find a better way to do this. What are we going to use that'll get people out of the way for sure? Let's give it a car horn. And so on the third day, they brought Minerva out. They turned it on and it woke up and it said, "Hi, my name is Minerva. Would you like a tour?" Somebody said yes. There was a big crowd of people around. It looked around and saw there was a big crowd of people. It said, "Excuse me, could you please move?" Somebody moved out of the way. Somebody else stepped in. And Minerva honked its horn. And sure enough, a bunch of people moved out of the way. And the robot, for the very first time, rolled forward about 5 feet. And then it ran into its arch nemesis, a teenage boy. And he realized that if he were to jump in front of the robot, he could get it to honk its horn. And so he jumped in front of the robot, and the robot would honk, and he'd jump out of the way, and another kid would jump in, and the robot would honk its horn. And after giving them about half an hour of playing Make the Robot Honk Its Horn, they turned it off and they took it away. And now they were in trouble. Because here was this multi-million-dollar project that they had spent tens of man-years developing. And they couldn't get it to move more than 5 feet. And so they thought about it for a while, and they finally settled on a solution that they knew was going to work. They gave the robot a face. And so now they brought the robot out and they turned it on and it woke up and it said, "Hi, my name's Minerva. Would you like a tour?" And somebody said yes. And there was a group of people around and it said, "Excuse me, could you get out of the way?" And somebody got out of the way and somebody else got in and it honked its horn. And the second time it had to honk its horn, it looked sad. And nobody wanted to be the one to make the robot look sad. And the robot gave its very first tour. Now, this solution cost them one red rubber band and about $22 worth of mechanical parts and servos. What's the lesson to take from this? It's these little things that we have to think about when we want to design robots that go out there in the world, about how people are going to respond to them. Those are the things that are going to make this successful. Those are the things that are going to let us demonstrate that these multi-million-dollar projects really do work. These are the things that are important to people. And that's what we are trying to spend our engineering time on now. Okay, so thank you guys very much for your attention and your willingness to dance.